Sekarang kita masuk ke bagian mekanika fluida. Dari referensinya buku Genkoplis ya. Referensi utama untuk OTK ini ada dari Genkoplis dan juga dari Mekip. Nah, sudah ada di kontrak, teman-teman bisa nyari. Pertama, untuk mekanika fluida kita ada hukum Bernoulli dan profil kecepatan dalam pipa. Jadi kalau dalam industri itu ada pipa ya. Pipa itu kan posisinya macam-macam. Ada yang tinggi, ada yang pendek gitu. Itu di setiap posisi energinya berbeda-beda. Energi mekanik ini adalah energi keseluruhan yang meliputi kerja, energi kinetik, potensial, dan entalpi ya. Nah, ini di persamaan ini bisa kita lihat ada energi kinetik, ada energi potensial yang ini ya. Ada energi dari perubahan tekanan, ada gaya yang dimaksud di sini kebanyakan terjadi adalah gaya gesek di pipa ya. Juga ada kerja. Tapi juga bisa jadi ada gaya-gaya lain yang kerja di fluida tersebut. Biasanya kalau energi itu ada masanya ya, setengah mv kuadrat gitu ya, setengah mv kuadrat. Jadi ini spesifik persamaannya, spesifik terhadap setiap satuan massa dari fluida. Kalau kita mau mencari energinya secara keseluruhan, ya kita kalikan dengan laju alir masanya. Gitu. Nah, ini menunjukkan neraca ya. Jadi di titik 2 dikurangi yang titik 1 sama dengan 0 atau sama ya. Inlet dengan outlet itu energinya sama secara total gitu. Karena ada hukum kekekalan energi di sana. Nah, dalam kasus tidak ada energi mekanik yang ditambahkan, nah, kerja ya maksudnya, dan tidak ada gesekan, persamaan Bernoulli bisa dituliskan sebagai berikut ini. Jadi nggak ada sigma F sama W-nya tadi. Yang sebelah kiri adalah yang di posisi 1, dan yang sebelah kanan ada yang di posisi 2 energinya ya. Ini bisa kita pakai ya dalam banyak situasi praktis. Banyak situasi yang bisa kita asumsikan di sana tidak ada gaya gesek, kehilangan energi karena gaya gesek gitu. Kalau ini adalah persamaan untuk menentukan laju alir massanya. Ya, densitas dikalikan dengan A ini luas penampang, kemudian P ini adalah kecepatan. Kalau Z tadi apa? Z itu ketinggian ya, ketinggian dari suatu posisi fluida dalam pipa. Contohnya yang sederhana di sini kita punya pipa horizontal. Pipa horizontal dengan ukuran yang berbeda. Ya. Kita asumsikan tidak ada kerugian karena gesekan. Di sini luas penampang 1 lebih gede daripada luas penampang di 2. Nah, otomatis nanti jika kita masukkan ya ke persamaan Bernoulli, kecepatan dan juga tekanannya akan berubah. Nah, dengan persamaan kontinuitas tadi yang laju alir massa, karena kerapatannya atau densitasnya sama ya, maka bisa kita tuliskan seperti ini. A1 kali V1, A2 sama dengan A2 kali V2. Ya. Jika A-nya besar, maka otomatis kecepatannya akan kecil. Jika penampangnya kecil, otomatis kecepatannya akan besar ya, untuk mengkompensasi persamaan. Nah, lalu bisa kita masukkan ke persamaan Bernoulli. Ini perbedaan energi potensial tidak ada, jadi bisa kita tuliskan 0. Ini kecepatan di 1, energi kinetik di 1 ya. Energi karena tekanan di titik 1. Kemudian ini dari persamaan kontinuitas dimasukkan ke sini. Lalu ini tekanan di titik 2. Sehingga bisa kita dapatkan persamaan untuk kecepatan di titik 1 dan kecepatan di titik 2. Ya. Jadi di sini, di dalam gambar ini ada alat ukur ya, ada alat ukur tekanan. Tekanannya bisa diukur, kemudian jika kita mau mencari kecepatannya, bisa dipakai persamaan ini. Ya, silakan, Mas
Mohon
Muhammad
maaf,
ya.
Bu.
Ya.
Ya, Bu. Mohon maaf. Untuk yang volume 1 itu, Bu. Yang 2 GC itu GC apa ya, Bu?
Oh iya, itu kayaknya typo itu. Maaf ya. Salah, itu typo. Iya, nggak ada itu.
Baik, Bu. Terima kasih.
Iya, sama-sama. Nggak ada ya gizinya, jadi cuma cuma 2 saja. Di persamaan ini kan nggak ada gizinya sama sekali ya. Oke, terima kasih pertanyaannya. Kita kalau teman-teman mau ngecek lagi, boleh dibolak-balik aja, ini persamaannya nanti akan ketemu ya. V1 dan juga V2-nya. Kemudian bagaimana profil kecepatan dalam pipa? Jadi dalam pipa itu kan silinder ya. Yang paling pinggir ada yang namanya dinding ya. Dinding yang bergesekan dengan fluidanya. Sehingga ada pengurangan energi di sana. Jadinya energinya, kecepatannya itu cenderung lebih lambat daripada yang di tengah. Gitu. Ini berlaku ya untuk keduanya, baik untuk aliran laminer maupun turbulen, fluida dalam pusat pipa bergerak lebih cepat daripada fluida yang dekat dengan dinding. Kemudian ini ada persamaan untuk menentukan kecepatan berdasarkan posisi ya. R kecil itu adalah jari-jari, R besar ini adalah jari-jari keseluruhan. Kalau R kecil ini posisinya dari itu ya, dari pusat. Gitu. Posisi dari pusat pipa. Ini ada grafik ya. X-nya adalah dV rho per mu atau bilangan Reynolds. Bilangan Reynolds ini menunjukkan yaitu alirannya laminer atau turbulen. Gitu. Nah, kalau di persamaannya ini dia dipengaruhi selain oleh kecepatan, juga oleh diameter, densitas, dan juga viskositas ya dari fluida. Kemudian ada Y-nya ini adalah kecepatan rata-rata per kecepatan maksimum. Rasio ya, rasio kecepatan rata-rata dibagi kecepatan maksimumnya. Kecepatan maksimumnya itu berarti 1. Yang di pusat pipa gitu ya, pokoknya kecepatan rata-rata itu rata-rata di semua posisi. Nah, kemudian ini adalah daerah laminer, kemudian ini adalah daerah turbulen. Di atas 2000 ya, bilangan Reynolds-nya itu biasanya turbulen. Jadi, kalau di yang laminer, itu kecepatan rata-ratanya lebih rendah. Nah, di sini ya. Tapi itu masuk ke daerah turbulen, dia naik ya, naik bisa sampai sini. Itu karena kalau turbulen itu lebih banyak daerah yang kecepatannya itu rata ya, hampir sama dengan kecepatan maksimum. Hanya yang di pinggir aja ya lambat gitu. Ini ya gambarnya. Nah, dalam banyak aplikasi teknik, hubungan antara rata-rata kecepatan dalam pipa dan kecepatan maksimum sangat berguna ya, karena dalam beberapa kasus hanya kecepatan maksimum pada titik tengah tabung yang diukur. Oleh karena itu, hanya dari satu titik pengukuran, hubungan antara kecepatan maksimum dan kecepatan rata-rata dapat digunakan untuk menentukan kecepatan rata-rata. Jadi, alatnya itu mengukur kecepatan maksimum yang di tengah. Sedangkan rata-ratanya kita bisa menentukan dengan menggunakan bilangan Reynolds tadi ya, yang grafik tadi. Karena kok kita nggak pakai yang maksimum saja, karena yang mengalir itu bulk ya, bulk itu secara keseluruhan gitu alirannya. Nah, kemudian kecepatan rata-rata pada seluruh penampang pipa adalah tepat 0,5 kali kecepatan maksimum di pusat, seperti yang diberikan oleh keseimbangan momentum untuk persamaan aliran laminer. Nah, sedangkan untuk yang turbulen, kecepatan rata-ratanya sekitar 0,8. Nah, tapi bervariasi tergantung bilangan Reynolds-nya. Ini ya gambaran dari kecepatan ya, profil kecepatan dalam pipa. Ini semakin ke dinding, dia semakin lambat ya, hampir 0 malahan kalau laminar. Kalau yang turbulen, dia karena lebih acak ya alirannya, jadi dia apa namanya, kecepatannya itu nggak selancip ini profil kecepatannya. Gesekannya itu jauh lebih kecil dibandingkan kecepatannya. Makanya banyak yang kecepatannya mendekati kecepatan maksimum. Tuh. Nah, ini untuk gambaran dari persamaan Bernoulli. Kita lihat lebih jelasnya ya di video ini. Ada animasinya ya, jadi lebih bagus.
Halo, perkenalkan, nama gue Egy Mulhan dari channel Egy Mulhan. Thanks to CuriosityStream for sponsoring this video. Watch thousands of documentaries and get access to Nebula for free when you sign up using the link in the description. Bernoulli's equation is a simple but incredibly important equation in physics and engineering that can help us understand a lot about the flow of fluids in the world around us. It essentially describes the relationship between the pressure, velocity, and elevation of a flowing fluid. It has countless applications. We can use it to explain how planes generate lift, or to calculate how fast liquid will drain from a container, for example. We'll explore these applications and a few more later on, but let's start by reviewing the equation itself. It was first published by the Swiss physicist Daniel Bernoulli in 1738, and it looks like this. The equation states that the sum of these three terms remains constant along a streamline. Each of the terms is a pressure. The first term is the static pressure, which is just the pressure P of the fluid. Then we have the dynamic pressure, which is a function of the fluid density, ρ, and velocity, v, and represents the fluid kinetic energy per unit volume. And the last term is the hydrostatic pressure, which is the pressure exerted by the fluid due to gravity. G is gravitational acceleration, and h is the elevation of the fluid, which is just its height above a reference level. This is the pressure form of the equation, but it can also be presented in the head form and the energy form. We can think of Bernoulli's equation as a statement of the conservation of energy. It says that along a streamline, the sum of the pressure energy, kinetic energy, and potential energy remains constant. This is really valuable information that can help us analyze a whole range of fluid flow problems. The equation does have a few limitations, which I'll cover later on in the video. But for now, the important thing to note is that it can only be applied along a streamline. We can define a streamline in steady flow as the path traced by a single particle within the fluid. Or more technically, as a curve that at all points is tangent to the particle velocity vector. Let's look at an example where we apply Bernoulli's equation to flow through a pipe which has a change in diameter. We want to use the equation to see how the pressure changes as the flow passes from the larger to the smaller diameter. Bernoulli's equation is usually used to compare the flow at two different locations, so we can rewrite it like this, with points 1 and 2 both being on the same streamline. There's no significant change in elevation between points 1 and 2, so the potential energy terms cancel each other out. And if we put all of the static pressure terms on one side, we get this equation for the change in pressure. If we assume that the fluid is incompressible, the mass flow rate at points 1 and 2 must be equal. This gives us what's called the continuity equation, which is just a statement of the conservation of mass. Mass flow rate is equal to the product of the fluid density, the pipe cross-sectional area, and the fluid velocity. So we can rearrange the continuity equation to obtain an equation for the velocity at point 2. The cross-sectional area, A2, is smaller than A1, which means that the velocity of the flow increases as it passes into the smaller diameter pipe. This is quite intuitive. By substituting this equation for V2 into Bernoulli's equation, we can see that since the velocity increases between points 1 and 2, the pressure between both points must decrease. This concept that for horizontal flow an increase in fluid velocity must be accompanied by a decrease in pressure is one way of formulating what we call Bernoulli's principle. It can seem counterintuitive because people often expect an increase in velocity to result in a corresponding increase in pressure. But it makes sense if we think about the conservation of energy. The energy required to increase the fluid velocity comes at the expense of the static pressure energy. Bernoulli's principle shows up in a lot of different places. We can use it to help explain how plane wings generate lift. Fluid flowing over an airfoil travels faster than fluid flowing below it. According to Bernoulli's principle, this creates an area of low pressure above the airfoil and an area of high pressure below it. And it's this pressure difference that generates lift. I'll cover lift and drag forces in more detail in a separate video. Bernoulli's principle also explains how Bunsen burners work. When the gas valve is opened, gas flows into the barrel at high velocity. Following Bernoulli's principle, this high velocity creates an area of low pressure in the barrel, which draws air in through the air regulator, allowing for more complete combustion of the gas. Several different flow measurement devices rely on Bernoulli's equation to determine the velocity of a flowing fluid. The pitot-static tube is one such device. It's often used in aircraft to measure airspeed. Here's how it works.
Begini caranya mencari makan yang hemat di GoFood. Order GoFood sekarang.
Belanja di Alpha Gift, gratis ongkir.
If we place a tube into a flowing fluid, like this, and we attach a pressure meter to the end of it, the meter will measure the pressure at the end of the tube. At this point, the fluid velocity is reduced to 0, so it's called the stagnation point, and the pressure measured by the meter is called the stagnation pressure. We can apply Bernoulli's equation between an upstream point and the stagnation point, and show that the stagnation pressure is equal to the sum of the static pressure and the dynamic pressure terms. All of the kinetic energy is essentially being converted into pressure energy at the stagnation point. If we add an outer tube which is sealed at the end but has holes further downstream, the outer tube will measure the static pressure of the fluid instead of the stagnation pressure. These two pressure measurements give us all of the information we need to determine the velocity of the flow. Another flow measurement device that uses Bernoulli's equation is the Venturi meter, which is an instrument used to determine the flow rate through a pipe. It works by measuring the pressure drop across a converging section of pipe. Say we want to determine the flow rate, Q, which is the velocity multiplied by the pipe cross-sectional area at point 1. We can easily rearrange the pressure drop equation we derived earlier when we looked at a change in diameter to get this equation for flow rate. All we need to know is the dimensions of the Venturi meter, the fluid density, and the pressures P1 and P2, and that allows us to calculate the flow rate. The Venturi meter has no moving parts and is a very simple and reliable way of measuring the flow rate through a pipe. The diverging section is longer than the converging section to reduce the likelihood of flow separation and keep energy losses low. Let's look at one more example where we can apply Bernoulli's equation. Say we have a beer keg, and we want to calculate how fast beer will drain when we first open the tap at the bottom. All we need to do is define our 2 points along a streamline and apply Bernoulli's equation. It's a gravity-fed keg with a vent at the top, meaning that it's not pressurized. The pressure at both points will be atmospheric, and so the static pressure terms cancel each other out. We can also assume that the keg is large enough that the fluid velocity at point 1 is close to 0. If we rearrange Bernoulli's equation and define the height between the beer level and the tap as h, we get this equation for the beer velocity out of the tap. Those were a few examples of cases where we can apply Bernoulli's equation to get some valuable information or to solve a problem. But to use it correctly, it's important to have an understanding of the limitations of the equation, which arise because of how it's derived. There are several different ways Bernoulli's equation can be derived. It can be derived based on conservation of energy, by considering that the work done on the fluid increases its kinetic energy. Or it can be derived by applying Newton's second law, which involves determining the forces acting on a fluid particle and applying F equals ma. Although I won't cover either derivation here, they do both make some assumptions that we need to be aware of, since they limit how we can apply the equation. Firstly, the derivation of Bernoulli's equation assumes that flow is laminar and that it is steady, meaning that it doesn't vary with time, like this. Next, it assumes that the flow is inviscid, meaning that shear forces due to fluid viscosity are negligible. This assumption is needed because viscosity would result in a dissipation of some of the fluid's internal energy, and so the idea that energy is conserved along a streamline would no longer apply. And finally, the derivation of Bernoulli's equation assumes that the fluid behaves as if it's incompressible. This is usually valid for liquids, but might not be for gases at high velocities. All three of these assumptions need to be valid if you want to apply Bernoulli's equation. Adapted versions of the equation which can be applied to unsteady and compressible flows do exist, although they're a bit more complicated. Being able to recognize when Bernoulli's principle is at play, or when Bernoulli's equation can be applied to solve a problem, is a powerful tool in any engineer's arsenal. If you'd like to see a few more real-world examples of Bernoulli's principle in action, you can check out the extended version of this video on Nebula. Nebula is a video streaming service built entirely by educational creators like myself. It's home to some of the best creators out there, including Real Engineering, Practical Engineering, and City Beautiful. So you can watch content from them and many others on Nebula, completely ad-free. All of my videos are on Nebula, without any ads, and in the version of this video on Nebula, I've replaced this sponsorship message with a few more really interesting examples of Bernoulli's principle. Then there's the growing catalog of exclusive Nebula originals that you won't be able to watch anywhere else, like Mustard's fascinating look at Imperial Japan's underwater aircraft carriers, or the logistics of D-Day series. And best of all, you can get access to Nebula for free when you sign up to CuriosityStream using the link in the description.
Marjan, bangkitkan harapan.
After the creation of boundary layer particles goes through, let us visualize it. Consider a fluid entering a circular pipe at a uniform velocity. A fluid in motion comes to a complete stop at the surface and assumes a zero velocity relative to the surface. That is, a fluid in direct contact with a solid sticks to the surface, and there is no slip. This is known as the no-slip condition. The fluid property responsible for the no-slip condition and the development of boundary layer is called viscosity. The layer that sticks to the surface slows the adjacent fluid layer because of viscous forces between the fluid layers, which slows the next layer, and so on. So, the flow region adjacent to the wall, in which the viscous effects are significant, is called the boundary layer. But in the blue region, there is no boundary layer surrounded, so the frictional effects are negligible, and the velocity remains essentially constant in the radial direction. This blue region is called irrotational flow region. As the fluid passes by, the thickness of this boundary layer increases in the flow direction until the boundary layer reaches the pipe center and fills the entire pipe. Remember, at first, water velocity is just a function of pipe length and pipe radius, but when the boundary layer fills the entire pipe, then velocity will just be the function of pipe radius. Keep that in mind. So, when velocity varies only on radial direction, then velocity profile develops, which makes calculation easy, as it only depends upon one direction. That is pipe radius. The region from the pipe inlet to the point at which the velocity profile is fully developed is called the hydrodynamic entrance region, and the length of this region is called the hydrodynamic entry length. So as you can see, the velocity profile, it have different velocity along the radius of pipe. For example, at the center of pipe, r equals 0, velocity is 4 meters per second, and similarly, at the complete radius of pipe, velocity is 0, which is due to no slip condition. You can see how the velocity varies radially, and if you plot every velocity as a function of radius, you will get an parabola. The velocity profile in the fully developed region is parabolic in laminar flow and much flatter, or fuller, in turbulent flow due to eddy motion and more vigorous mixing in the radial direction. Please subscribe for more fluid mechanics animation.
Pakai Gomar tinggal pilih toko, pilih produk, bayar. Have fun Gomar!
Consider a hypothetical experiment in which a material.
Ya, itu tadi ya untuk Bernoulli dan profil kecepatan dalam pipa. Kemudian ini ada latihan untuk teman-teman diskusikan secara berkelompok ya. Kita buat kelompok isinya 4 orang. Kalau ada yang ganjil berarti dibuat 3. Siapa yang mau jadi koordinatornya? Kelas UTK 1 ini? B.